In this section, we'll take a look at an introduction to the concept of the derivative.
Recall an expression that you have seen in algebra. The difference quotient of a function The difference quotient of a function is defined as follows. You take your function and evaluate it at some value x plus h. You subtract away the value of the function at some value x and divide the entire expression by h. So here we have the difference quotient of the function. Here in this case the function f of x. Now this is an expression in its own right. However, it can be used to represent a physical concept. That is to say, we can think about it what it looks like on a graph. So for a moment, consider a function f of x, and it doesn't actually matter what function we have. So here I'm going to draw an arbitrary curve, something like this. And here we can assume this goes on forever or is just that long. It doesn't make a difference. All right, now, when you have a function, you can assign an x value, which you're going to plug into your function, and that'll give you a y value, or an f of x value. After all, y equals f of x is a common way of writing that function, or rather, common way of writing the graph of that function. So here I can say, let's say that's my value of x. And if I go ahead and plug that in, it's going to give me a value for, so that's going to have a y value, which we can call f of x. And in fact, here I can even label that. Right? If that's my x value, then my y value is this one over here, f of x. Okay. Now, let's say I plugged in another number. You say, okay, like this one over here, you can call this one what, x2, you want to call it w, you want to call it something else. Well, we could, of course, but what I'm going to do is I'm going to choose to call it something relative to the first value x here. So I'm going to say, okay, this number is some other number that's close to x. That's not terribly far away. So how far is it from x? Well, let's say it's a distance of h. Why h? It doesn't have to be h. That's just a common symbol used whenever we're dealing with something like this. A small distance, we'll call it h. So we can call this x2 or w, but another way you can say it is, well, it's x plus that extra distance. So you can call that x plus h. All right, well, if you plug in x into your function, you get f of x. If you plug in x plus h into your function, well, you're going to get f of x plus h. So from this illustration here, we can assign a physical interpretation to the difference quotient. You're saying, well, I'm taking the difference in these two values. Okay, so that's the difference in f of x plus h minus f of x. That's how far it is vertically from this point to this point, how far up you go. Now, h is the distance across, how far left and right you go. So this is a quotient of how far up you go versus how far right you go to get another point. Well, that's the concept of slope. So what that means is, if I connect these 2 points with a straight line, the slope of this line is the difference quotient. So here, the slope of the line that passes through x comma f of x and x plus h comma f of x plus h is the difference quotient. it is f of x plus h minus f of x over x plus h minus x. Or here, since these x's subtract away to give you 0, really that's just f of x plus h minus f of x over h. All right, so that's a physical interpretation of the difference quotient. It's the slope of a line which passes through those 2 points on that function, on that curve. And now we're going to ask a question now that we couldn't really ask, at least not fully, in an algebra class. What happens as we have h get closer to x? You say, well, we can ask that. I could just pick a smaller h. If, for example, if h was 5, now I can pick 3. Or I can pick 1 or 1/2. Okay, well, let's say I didn't want it to be 3 or 1 or 1/2. Let's say I wanted this to be this point. Let's say I didn't want these to have any distance. Well, the problem with that is h would be 0. If there was no distance between these, h would be 0. And of course that's undefined, because divided by 0 is undefined. Okay, well, why would I even want to do that in the first place? Why would I care about having, that doesn't even make any sense. What does it mean to have the slope of 1 point? Well, in order to make sense of that, let's see what happens if we make the slope of a line, if we find the slope of a line that's not separated by 0 distance. Let's just have it slightly closer. All right, so instead of having the slope of the line from here to here, let's say we have the slope of the line between here and here. Let's just say our h was closer. It's smaller, but it's not 0. Okay, well then you'd have the slope of this line right here. And if you made it even closer, you'd have the slope of this line right here. Notice that the closer these two lines get together, the closer these 2 points are, right? The smaller h's, the closer these 2 points are. What happens if I put them extremely close together? Like here, if I were measuring this maybe 1 millimeter apart, extremely close together. Well, now it's hard for me to even tell that there's any space in between them. Okay, well, what does that line look like? The one where the 2 points are super close together. Well, that basically looks like a line that only touches the graph at 1 point. Now, of course, we know it's at 2 points because the 2 points are very close together, but it looks like it's touching it at only 1 point. This is what's called a tangent line. So before, we had a line that was passing through 2 points on a curve. That is called a secant line. Okay? So a secant line passes through 2 points on a curve, but a tangent line is the line that touches the curve only at 1 point. Well, that's at least a physical interpretation of that. Right? What is a tangent line? It's the line that touches that curve at only 1 point. You say, well, I could do that by just doing this, couldn't I? Couldn't I just cross right here? That would only cross at that 1 point. Okay, so by saying the tangent line only crosses at 1 point, that is not a formal definition. Right? That's a way of describing it. But of course, that description is not perfect because, again, we could just draw this line right here, and that would only touch at 1 point. Okay, so what is the formal definition of a tangent line? It's this process. It's the process of taking a secant line and letting the 2 points get closer and closer together. In other words, let h be 0. You say, but I can't do that. I can't let h be 0. Because if h is equal to 0, dividing by 0 is undefined. Okay, then we do the next best thing. We take the limit as h approaches 0. This is called the derivative of a function. Definition. Let's begin with a function. Let f of x be a function. The limit as h approaches 0 of f of x plus h minus f of x over h, that is denoted with the notation, in fact there's several notations. There's a few different ways of writing the derivative, but the one that's most common is usually the one that's the simplest, and that is this right here. You're going to write f of x. That's not a power 1. It's not a number 1. It's like a little tick mark. This is read as the derivative of f, or is also sometimes read as f prime. So here, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? This is the derivative of f at x. Because notice that at x, you're doing it at this point. Here, we're getting closer. We're getting h smaller, which means these points are getting closer and closer together right here. If we did the same drawing but up here, well, that would be a different result. That would look like a different line. So here, we're looking at the derivative of f at that particular point. Okay? Whenever you have this notation, again, this little tick mark, it's not the number 1. It's just like a little dash. And this is read as f prime. F prime. F prime is a notation for the derivative of f at x. So f prime at x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. This right here is what it is. Right? F prime of x is this limit. Now, there are plenty of ways to interpret what this limit is. One physical interpretation of the derivative is to say it's the slope of the tangent line. And that will be one way of helping us define the tangent line. It's the line that has that slope and which passes through that point. But there is one important note here, and that is this is just a function. That's all it is. It can be used to find lots of things. It can be used to find slopes of tangent lines, among other things. It can be used to find instantaneous change, velocities, and accelerations. It can be used to find lots of things. But what this is, it's just a function. That's all it is. Right? And it's a function defined by a limit. Now, there is one little stipulation here. We have seen in the past that there are limits that we cannot find because it's possible the limit does not exist. It's possible that the limit from the left and the limit from the right are different from each other, for example. So here, the little stipulation we do have to add is provided that this limit exists. It is possible that the limit does not exist, in which case you would just say the derivative doesn't exist either. Provided that this limit exists. So let's use this definition to find the derivative of a few functions. Let's begin with probably the simplest function to work with, and that's a polynomial. Polynomial functions are the easiest ones to find the derivatives of, and from there, other ones can be a little more complicated. All right, so here we go. Let's begin with the limit. Let's just start off with a function. So let's take f of x to equal to, and I'll start off very simply with just x squared. All right, so now the question is, we're going to go ahead and find f prime of x. Okay. Here, we're going to do every problem using the definition. Now, in full disclosure, there are some shortcuts for certain functions. In particular, there's a nice shortcut for polynomial functions. However, those shortcuts depend on the kind of function you're dealing with. You have a shortcut for a polynomial function. You may have another shortcut that works for radical functions. You may have another shortcut that works for logarithmic functions. Trigonometric functions, there's not really any shortcut. You just have to memorize those in some cases. And there are other functions that there is no shortcut for. Right? You just have to go through. For now, we're not going to consider any of those shortcuts. We're going to start just from the definition. Right? After all, this is just an introduction. The shortcuts are a little bit more of an advanced use of this material. So right now, we're going to do everything just from the most basic definition. Here, f of x is equal to x squared. We're going to go ahead and find f prime of x. All right, so let's go ahead and do that. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. All right, well, f of x plus h is what happens when you take this function and replace the x with an x plus h. So that'll be x plus h squared. Minus the original function, which we saw was x squared, that was given to us, over h. And we're going to take the limit as h approaches 0. Here, don't forget to write the limit at each step, because the limit itself is an operation. Right? It's f prime of x is not the difference quotient. This is incorrect. F prime of x is the limit of the difference quotient. Without the limit, that is incorrect. So here, the limit as h approaches 0 of this expression. Well, let's simplify this expression. That's going to be the limit as h approaches 0 of, we can expand this by squaring everything. That'll give us x squared plus 2xh plus h squared. That's what happens when you multiply x plus h times x plus h. And then don't forget you have minus x squared right there over h. Note that these two terms subtract to give you 0, x squared minus x squared. So this is the limit as h approaches 0 of 2xh plus h squared over h. Notice that h is the common factor in that numerator. So you can write this as the limit as h approaches 0 of h times 2x plus h over h. And notice that here you can divide these two away. Well, you can divide these two away as long as they're not 0 over 0. Oh, but since you're taking the limit as h approaches 0, that means h is never actually 0. It's 0.1 or 0.01 or negative 0.0000005, but never 0. Right? That's what we mean when we take a limit as h approaches 0. H is close to 0, very close to 0, but never 0. So since these are never 0, it's just some number divided into itself, which means they can divide away. So that's going to be the limit as h goes to 0 of 2x plus h. But now, as h approaches 0, there's no h here. So nothing happens to the 2x. It just stays 2x. And h, well, when you take the limit as h approaches 0 of h, notice that's a polynomial. H, that's like saying h to the first power. You just plug that number right in. So that h is going to be replaced by a 0. So you're left with 2x plus 0, which is just 2x. That's the derivative. The derivative of x squared is double x. Now, you might be slightly confused by that result. After all, didn't we say that that's the slope of the tangent line? But that's not a constant. How can the slope be variable? Well, it makes sense when you consider the fact that the slope will change depending on where on the graph you are. Here, the slope will be one thing, but if you find the slope over here, that's another thing. We can see that a little more clearly if we actually graph the function f of x equals x squared. Okay, so there's the graph of f of x equals x squared. This derivative, the slope of the tangent line, is a function. Because, for example, what does f prime at 0 mean? Well, that means what's the slope of the line tangent to the curve when x is equal to 0? Oh, well, that's going to be 2 times 0, which is 0. And if you look at your graph, that makes perfect sense. Because the tangent line that touches the curve at the origin when x is equal to 0, hey, that's a perfectly flat line. Look at that. Okay, well, what if I said I want f prime at 1? Well, that would be 2 times 1, which is 2. Well, that makes sense too, because right here, when x is equal to 1, if I take the slope of the tangent line right there, yeah, that's a small positive slope. Well, what if I wanted the derivative at a bigger number? Let's say I want f prime at 2. Well, that's going to be 2 times 2, which is 4. Oh, well, when x is equal to 2, I can follow that up to my curve. So there's my point when x is equal to 2. And the tangent line there is going to be steeper. Oh, yeah, that looks like a slope of 0. And that's a line with a slope of 1. And that's a line with a steeper slope. So that would be a slope of 4, right? So slope of 0, 2, and 4. But what if I wanted to find the slope at -1? Well, that's 2 times -1 is -2. And yeah, that looks about right. Because if I take my x value to be -1, if I follow that up to my curve, that puts me at this point. And the tangent line at that point, the line that hugs along the outer edge, the one that touches only at that one point, yeah, that's definitely got a negative slope. So here, the slope is variable. That makes sense because as you move along your curve, it will change your slope. Slightly more familiar way of understanding this concept of the slope changing is consider my friend here, Eddie. He's a small cyclist, a small die-cast metal cyclist. Just happened to be sitting here on my desk. Let's say he's traveling right here, and he's going down a hill, very steep, and he's going to climb out of this, right? So right now he's going downhill. And right here, he is just flying because he's facing down a very steep hill. But as he goes down, notice that he's kind of leveling off. When he's at the bottom of the hill, he's facing straight across. So the slope for him, at least in this moment in time, is 0. But then as he starts to climb, okay, I know the slope is changing, but at this exact moment in time, when he's sitting right here, his slope is positive. And as he keeps climbing, that slope is getting higher and higher. So one way you can think of this from a physical standpoint is, as I am riding a bike down a hill and then back up, my slope is downhill very steep, but it's getting less and less steep as I reach the bottom. And when I reach the bottom, hey, for just a second, I'm not going up or down. I have a perfectly flat slope. Oh, but a second later, I'm going back uphill. And now my slope is getting steeper and steeper and steeper as I go. So what is the derivative? It's just a function. But one thing that it can represent is it can represent the slope of the tangent line. Another thing it can represent is an instantaneous slope. Yes, I know the curve changes, but at this exact moment in time, what's the slope? Okay. So here we have one example of that. But now let's see that again for a few other functions. Let's go ahead and find the derivative. So let's say f of x is equal to, let's take the square root of x. Let's say f of x equals the square root of x. Let's go ahead and find, fid. Let's go ahead and find f prime of x. Okay. All right, same thing. We're going to start off with the definition. F prime of x is equal to is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That is to say, it is the limit as h approaches 0 of, all right, go ahead and take your x plus h and replace it where your x was, like that, square root of x plus h, minus, okay, now use the original function the way it started, like that, over h. Now, as much as I'd love to just plug in h equals to 0, I know I can't do that because that'll give me 0 here. Right? In fact, it'll give me 0 on both parts, 0 over 0. Okay, well, I can simplify this. We have seen that if you take an expression that has a square root in either the top or the bottom, and you cannot plug in a value to take a limit, often what is required is you can rationalize the part that has a square root, either the numerator or denominator. In this case, the numerator. So what we're going to do is we're going to rationalize the numerator, the one that has the square roots, by multiplying the numerator by its conjugate, square root of x plus h plus square root of x. And whatever you do on the top, you're going to do the same thing on the bottom. And after all, you've just done the same thing to top and bottom. So really, you've just multiplied by the number 1. And multiplying by the number 1 never changes anything. Okay, so this is still the same result, but now let's go ahead and clean it up and see what, if anything, that has simplified. All right, so in our numerator, square root of x plus h times itself, that's square root of x plus h times itself, that's to say it got squared. And then right here, that's going to be plus the square root of x times the square root of x plus h. And then right here, we have a minus square root of x times square root of x plus h. And then here you have a negative times a positive, so that's a negative. Square root of x times another square root of x is square root of x squared. In the denominator, I'm not going to bother multiplying it out. Whenever I'm rationalizing, I multiply out the one that needs to be rationalized. The other one, I'm going to leave that alone in the hopes that something will simplify it away. And quite often, for many of the functions that we'll see, yes, something will simplify it away. All right, notice that your numerator can be simplified a lot. These two expressions are opposite of each other. So when you add them together, you get 0. Here, the square of a square root, well, that just gives you the argument, the x plus h. And same thing here, the square of a square root just gives you the argument, the x. So this is going to equal to the limit as h approaches 0. Here, that square root is gone, as is that square. You're left with just x plus h. All of these are gone. And here you're left with minus x, since that square root and that square are gone, over h times square root of x plus h plus square root of x, like this. Notice that in your numerator, these x's now subtract away. X minus x give you 0. So you are left with the limit as h goes to 0 of h over h times square root of x plus h plus square root of x. Now notice that as long as h is not equal to 0, these two can be divided away. And since you're taking the limit as h approaches 0, we know it gets close to, but is never actually equal to 0. So since these are not 0 over 0, they are just some number over itself, those can be reduced to 1. So we are left with the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. But now as h approaches 0, this 1 is a constant. It's not affected. It's going to stay the number 1. As h approaches 0, this x doesn't have an h in it. So it's going to stay the way it is. Here, as h approaches 0, anything that doesn't have an h is going to stay the way it is. But now this part right here, well, that's the square root of a polynomial. And see, the thing about a polynomial is that when you take a limit, as something happens, all you have to do is plug in that number. So right here, what we need to do now is plug in h is equal to 0. And so this gives us 1 over the square root of x plus 0, which I can just write as the square root of x, plus the other square root of x that's already there, square root of x plus square root of x, that's double the square root of x. So that is our result. If you begin with the function square root of x, the derivative of that function is 1 over 2 root x. That can be interpreted as the slope of the tangent line at different values of x. That can be interpreted as the instantaneous slope, the instantaneous rate of change at different positions along a path. It can be interpreted as all kinds of things, but it is this function. All right, so go ahead and give this a try. Let's begin with a function. Here we go. Let's say f of x equals 4 over x. Go ahead and find f prime of x. Okay. Pause the video and give that a try. Give yourself whatever time you need, and once you are done, go ahead and unpause the video and we can go through that together. All right, so let's take a look. We're going to begin with the definition. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Eventually, you'll be able to just recite that. You'll use this so often, that just gets burned into your memory. It's the limit of the difference quotient. All right, so now for this particular example, it's going to be the limit as h approaches 0. You're going to take x plus h and use that to replace your x. So it's going to be 4 over x plus h minus the function with just the x in place. So minus 4 over x. And that's going to get divided by h. Okay, well, I'd love to plug in h is equal to 0, but that'll give me 0 over 0, in fact. Okay, so that means I have to simplify. Well, here, this is complicated because that's a complex set of fractions. It's a fraction and another fraction within another fraction. So I think the first thing I want to do to simplify is to just go and combine all of this as one fraction. So let's give these a common denominator. I will multiply over here by x on the top and bottom, and I'll multiply over here by x plus h on the top and bottom. And what that'll do is it'll give me a common denominator of x times x plus h. All right, so that's equal to the limit as h approaches 0 of, that's going to be a 4x minus, that's going to be a 4x and a 4h. Right? Now, this negative is going to distribute. That's negative 4 times x, and then that's negative 4 times h over your common denominator, x times x plus h. Once again, 4x minus 4x minus 4h over your new common denominator. Now don't forget, that's just the numerator. The whole thing is being divided by another h. That whole thing is being divided by another h. Okay, so now some stuff simplifies at least. Notice right here, 4x minus 4x, those two subtract away to give you just 0. And so you're left with the limit as h goes to 0 of negative 4h over x times x plus h all over h. But notice I'm dividing by h right here. And dividing by expression is the same as multiplying by its reciprocal. So if I'm going to say I'm going to take this thing right here, which is the same as this thing right here, if I'm going to divide it by h, that's the same as multiplying by 1 over h. Dividing by an expression is the same as multiplying by its reciprocal. But if I write it that way, it becomes a little more apparent that those h's divide away. Because after all, as long as they're not both 0, which they're not, they're close to 0, but they're not 0, then those can divide away. So this gives me a limit as h approaches 0 of negative 4 times 1, which is just negative 4, over x times x plus h. But now I'm taking a limit. Notice there's no h in the numerator, so that's just going to stay the way it is. And here I'm taking the limit of a product, which means I can take the limit of each piece on its own. This one doesn't have an h, so that's going to stay the way it is also. Oh, but this one does have an h. Oh, notice that it's a polynomial. When you take the limit of a polynomial, you can just plug the number right in. So here I can just plug in h is equal to 0. So this will give me negative 4 over x times x plus 0, which I think I'll just write as x. And since x times x is x squared, I can write my result as negative 4 over x squared. And there we go. F prime of x is the function negative 4 over x squared. Y equals negative 4 over x squared. That is the limit of my difference quotient. It is my derivative. Note that in application, this can be used to mean a lot of things. It can be interpreted a lot of different ways. But in essence, all it is a function. If you wanted to find the derivative at a particular number, you could just then plug in your number. So as a follow-up, we can ask find f prime at 3, find f prime at negative 2. All right? So go ahead and give that a try. Pause the video for a moment and find those results. You can, of course, use the results of the previous exercise, and these are fairly short. So go ahead and pause and find those results. All right, just like in our previous problems, once you know what the derivative is, you can always substitute in any value you like to find the derivative at that particular point. So we can say, all right, we know the derivative for all values of x. So if you want it for a particular value of x, just go ahead and plug that in. So f prime at 3 is going to be negative 4 over 3 squared, which is going to be negative 4 over 9. If we want to find f prime at negative 2, that's going to be negative 4 over negative 2 squared. Now, you're squaring the negative, so that makes that a positive. So that's negative 4 over positive 4. Or in other words, it makes it negative 1. And there we go. It looks like our slopes are easy to find at any particular value once you know what the function is. All you do is plug them in. All right. For our last example, we're going to take a look at a simple application of the derivative. Okay. This is going to be something that looks like it comes right out of a physics book. All right. So a ball is thrown straight up from a rooftop. So you're not on the ground, you're actually up on a roof somewhere. It's thrown straight up from a rooftop that is 200 feet high. It's going to be thrown up with an initial velocity, the speed at which the ball left the person's hand or left the launcher or left whatever it was throwing it, was 60 feet per second. With an initial velocity of 60 feet per second. All right. Here we have a function. We're just going to give you this one, the position function. So S of t is referred to in many physics books as the position function. It's going to tell us how high up our ball is. So here, if you evaluate the position function, here t is time. So if you plug in t is equal to 7 and it gives you 400, that means after 7 seconds, it's 400 feet high. Okay. Here we're not going to talk about how to derive this. This is something best left for a physics course. Here we're just going to give the equation. It's going to be negative 16t squared plus 60t plus 200. Here you'll notice the number 200 and the number 60. That is your initial height, and that is the velocity at which it left the person's hand. And here, this is a constant that has to do with the gravitational acceleration on Earth. It changes depending on where in space or where what celestial body you're near. But in any event, that's your equation. All right. So now the question is, find the instantaneous velocity. In other words, the velocity at that exact instant, at that exact moment. Instantaneous velocity of the ball at 2 seconds. In other words, when t is equal to 2. Here t is measured by seconds here. All right, so the derivative can be used to find all kinds of things. It can be used to find slopes of tangent lines. It can be used to find instantaneous rates of change. That's what this is, by the way. This tells you your position. And I'm looking for velocity. Well, that's what velocity is. Velocity is how quickly your position is changing. If you're traveling at 40 miles an hour, that means that your position is changing 40 miles every hour, literally. So the change in your position is given by your velocity. So when we ask for the velocity, we're really asking for the derivative of the position function. So here, the velocity function, v of t, is equal to the derivative of the position function. This is a sentence, and this is a note that you'll see in physics books all over the world. You know? In fact, s and v are the common functions, the common letters that are used. All right, so really right here, even though this is an application, really what we need to do is we need to find the derivative. Okay, well, we know how to do that. This we may or may not know a lot of physics, but we certainly know enough math to pull off this part. Here, s prime of t, by definition, is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. All right, well, we can do that. That's going to be the limit. Let me put it down here. That's going to be the limit as h approaches 0 of, I'm going to take x plus h and replace my t's with x plus h's. Right. Oh, you know what? Here, my functions are t's, so maybe I shouldn't use x. I should use t. It doesn't make a difference. After all, it's just the label for the variable, but I should be consistent. Here, I'm not using x's for anything. I'm using t because I'm measuring time. Okay, so f of t plus h. It won't change how everything works. I'm just using a different letter. So right now, I'm going to replace all my t's with t plus h. Okay, so that's going to be negative 16 times t plus h squared plus 60 times t plus h plus 200. So that's my f of t plus h minus my f of t, that's the original function, negative 16t squared plus 60t plus 200, all divided by h. Okay. Well, we can simplify this by distributing and expanding and combining like terms. So let's go ahead and do that. This is going to be the limit as h approaches 0. We can expand this. That'll give us t squared plus 2th plus h squared. But then we're multiplying that by negative 16. So that'll be negative 16t squared minus 32 th minus 16h squared. So here I've taken t plus h times t plus h and multiplied by negative 16. Now for this one, I'm going to distribute my 60. So 60 times t plus 60 times h. And then your 200, that's a constant, so it's just going to stay the way it is. But then I have minus negative 16t squared plus 60t plus 200. All of that over h. Now, from here, you notice that several of your terms are now redundant. They cancel out. Negative 16t squared minus itself is 0. So that's 0. It's gone. If I take 60t minus 60t, that's 0. So those are gone. And 200 minus 200, those are gone. And that's it. Nothing else combines. So let's rewrite what we now have. We have the limit as h approaches 0 of negative 32th minus 16h squared plus 60h. That's it. Only those three terms are left in the numerator. In the denominator, we're left with h. Notice that h is a common factor of the numerator. So we can now write this as the limit as h approaches 0 of h times negative 32t minus 16h plus 60. I factored out an h. Here I factored out 1h, which still leaves me 1h. And here I factored out an h. And now, because h is not 0, it's only approaching 0, h over h is not 0 over 0, which means it is valid to divide them away. So we're left now with a much simpler limit. We're now left with the limit as h approaches 0 of a polynomial, negative 32t minus 16h plus 60. And the thing about a polynomial is that if you're evaluating the limit as h approaches 0 of a polynomial, all you need to do is plug in h is equal to 0. So here that's going to give, well, negative 16 times 0 will be 0. This will go away. And these other two don't have an h, so they'll stay the way they are. So that's going to give us negative 32t plus 60. So this is the derivative. This is what's called the velocity function. If you take the position function and take its derivative, that tells you how quickly your position changes. Or in other words, it tells you your velocity. Okay, so this function gives me velocity. Oh, but my question was I want the velocity at 2 seconds. Well, once we have the function, you can always evaluate at any number you like. So the question is to find the velocity at 2 seconds. Okay, let's find v of 2. Let's see here. Oh, you know what? Let me do 1 second because 2 seconds won't make any sense. Oh, actually, yeah, that's fine. Let me go ahead and say v of 2. Well, we'll just plug in the number 2 right here. So it's going to be negative 32 times 2 plus 60. Okay, so that's going to be what? Negative 64 plus 60 is negative 4. Now you might wonder, how is that a negative? How does that make any sense? Well, what happened is you're on a building, you're standing right here, and you're going to throw the ball up. But eventually it's going to start to come back down. So all this means is after 2 seconds, it's already starting to come back down. It's coming down at a speed of, here everything's being measured with respect to feet and with respect to seconds. So here the velocity, when you first threw it up at this exact moment, the velocity is 60 feet per second. In fact, you can even check that. If you plug in time equals to 0, in other words, no time has passed since you've thrown it, that's 0 plus 60, which is 60, which that was what was given to you. 60 feet per second was your initial velocity. After 1 second, 60 minus 32, that's 28. Notice it's slowed down quite a lot, from 60 to 28. And then after 2 seconds, it now has a velocity of negative 4. That means it's got a speed of 4, but it's coming back in the opposite direction. So after 2 seconds, it's already starting to come back down. If you plug in 3, 4, and 5, you'll notice that it's speeding up as it goes back down toward the ground. So here, velocity equaling negative just means it's moving in a direction that's opposite of the direction that it originally started in. We threw it with 60 feet per second going up, and after 2 seconds, it's going 4 feet per second going back down. It doesn't mean it'll stay at that velocity. It'll pick up speed as it drops, but at that exact moment in time, when t is equal to 2, it is going down back toward the earth, back toward the ground at 4 feet per second. So that's our answer. The velocity is 4 feet per second down toward the ground. And that makes us happy. The velocity is 4 feet per second down towards the ground. All right, so that's it. That brings us to the end of our topic as well as the end of our section. When you compute a derivative, we are doing everything in this section by definition. Note that the application of a derivative can be used to find rates of change. In this case, the rate of the change of position, namely the velocity. It can be used to find the slope of a line that's tangent to a curve at a particular point. But those are just applications. What is a derivative? The derivative is the limit of the difference quotient. And that's all it'll ever be. If anybody has any questions, comments, or problems, please make a note of those. Reach out, and I hope everyone has a nice day.